All right. Hello, everyone. Welcome to ECE 20002 for today. I posted the exam on grades just minutes ago, so those are available. Procedurally, again, I want to remind you that we'll have quiz 4 coming out this weekend. Homework 4 was due last night. So you should be able to see homework 5 now in Brightspace. Also posted was the exam 2 equation sheet. So you can see the equation sheet you'll get for exam 2, and you'll get a table sheet that'll go behind your equation sheet on the exam. So you'll be able to separate, two pages of equations plus a third page with tables. Before we begin, do we have any questions about content or anything of the sort? As a reminder, if you would like to discuss your exam grade in more detail, that's what office hours are for. If you can't make regular office hours, please use an appointment. Hints on the quiz. Pay attention to what I say. I don't really have anything more specific yet for this week's quiz. You'll probably see something related to poles and zeros. You'll definitely see some stuff related to the Laplace transform on it. These new. I'll post the exam solutions later today. But if you want to specifically discuss what you got wrong on the exam and discuss points or grading or things like that, please use office hours or make an appointment for extra office hours. So that's the policy I believe was laid out in the syllabus. And you'll have 1 week from today to post to request any regrades. So please do that if you need it. Any other questions? Okay. Let's go ahead and start lecture. So last time we started lecture set 5 with a discussion of the poles and zeros of a system. The poles are related to the natural response of the circuit, poles being the roots of the denominator of a rational transfer function. And they give rise to the natural response of a circuit. They also determine stability through the specific stability criteria we call BIBO stability, bounded input, bounded output. So for a bounded input, one that exists in absolute value less than or equal to a certain bound, you always get an output that is bounded for all of time. Let's see. So in order to be BIBO stable, you must have all poles within the left half plane. That does not include the imaginary axis itself. The imaginary axis poles on it are considered to be BIBO unstable. The more precise term would be marginally stable. However, we consider marginally stable cases to be BIBO unstable by definition in this class. So be prepared for that. And then remember, the presence of any pole in the right half plane will cause your system to be BIBO unstable, for sure. The zeros don't have nearly as much interesting going on with them. They are the roots of the numerator of a rational transfer function. They just say if you have a input that matches the functional form corresponding to a 0, then you just get no output in your forced response there. And remember, the transfer function being 0 at a given place means that, for an impedance type transfer function, it's a short circuit. For an admittance type transfer function, it's an open circuit. And then for a voltage gain or current gain type transfer function, it means there's zero transmission. So there's zero output voltage or output current under that condition. Then we started talking about resonance. So, resonance is a somewhat difficult phenomenon to describe, but, the definition, which courtesy of Wikipedia, says that it's the phenomenon that occurs when you have an input near a natural frequency of a system producing an output many times larger than the input. So we call that frequency the resonance frequency. And in circuits, it's associated with the interaction between inductors and capacitors, the interchange of magnetic energy for electrical energy, and vice versa. So, and then mathematically, the way it manifests itself is when the impedance or admittance of electrical components cancels out the impedance or admittance of another, specifically the imaginary components, reactance, and susceptance. So we looked at the series LC circuit as the first example. So we know omega naught is equal to 1 over square root LC. And, it's going to give rise to a natural response of B cosine omega naught T plus phi. And then we worked it out where we looked at the impedance, and then we put it into phasor form by saying S is equal to just J omega. So the impedance is J omega L minus J omega C. But since omega naught is 1 over square root LC, when we work it out mathematically, we get that, the impedance is 0 at that point. So that means there would be an infinite current for finite voltage input in this, perfect LC tank circuit without any resistance in there. So in this case, the resonance frequency is a natural frequency. Then we looked at the next little bit harder example, which would be a series RLC circuit. So its transfer function, 1 over RS plus SLS plus 1 over SCS. So when we look at the, and that's the transfer function relating the series current to the input voltage. Now with phasors, when we look at this, we get that at the natural frequency, the imaginary component will go away, that associated with the inductors and capacitors, and we're left with just the series resistance RS. So again, the resonance frequency is the natural frequency, and the series inductor and capacitor behave like a short circuit. And then as the counterpart case, by duality, we'll look at the resonance in a parallel RLC circuit, and we'll get that Yin of S is equal to 1 over Rp plus J times quantity omega C sub P plus 1 over omega L sub P. Except that plus should be a minus sign. That's one of the mistakes I made in the lecture. And then Yin, that other mistake, is just going to be 1 over Rp. So again, resonance frequency is just natural frequency, and it behaves as an open circuit. And then we're going to look at more complicated examples, because why do we bother carrying around the extra notation of omega R and omega C, or omega R and omega naught? Well, it's because in most circuits that don't have all series or all parallel elements, omega R is not equal to omega naught. And as you add resistances to a circuit, it stays a second order circuit, but you can get a arbitrarily complicated transfer function. What questions do we have so far? So resonance frequency is basically the frequency at which the system is resonant. So it's where the imaginary part of impedance or inductance goes away, depending on or impedance or admittance goes away, depending on what you're looking at for your transfer function. Whereas the natural frequency is basically, it's the sinusoid you get when you excite the circuit, when it's undamped. So if you just had L and C, it would be the sinusoid you get just by the presence of L and C wanting to oscillate at a given frequency. Does that answer your question, AJ? Good. So, it makes sense that these are related quantities. We've really only talked about, two frequencies related to RLC circuits. One is an undamped natural frequency, the other being the damped resonance frequency. And of course, you have the attenuation sigma p involved as well. But we're going to see that for a more complicated topology, we're going to have to deal with omega r not being equal to omega naught. So let's look at one of those circuits, first new slide of the day. So slide 16. So this would be a parallel series type circuit. So the way I named them, and this is not standardized at all, is, the majority, we have one component in parallel, and then there's a special case of the other parallel branch containing series components. So it's a parallel of a series. So this is a C parentheses LR. Again, that's definitely not standard notation. So just a reminder that this capacitor is in parallel to a series inductance and resistance. So now this is phrased more as a design problem. Choose the value of LS that causes a resonance for a sinusoidal input with radial frequency omega 1. So now we know what the input frequency is. We want to make the circuit resonate. So we're going to find the admittance of the circuit with phasors. So, by looking at the admittance, looking to the right here, we're going to see the admittance of the first branch, which is going to be in phasor land j omega 1 c sub p. And then we'll see the admittance of this other branch, which is 1 over its impedance, which is 1 over j omega 1 ls plus rs. So we can simplify the admittance by using the complex conjugate. So we'll multiply top and bottom of the right side of the right term by rs minus j omega 1 ls. And then, it's basically a factors like a difference of squares in complex numbers, or it's just a sum of squares in real numbers. So we'll get rs squared plus omega 1 squared ls squared. And then in the numerator, we'll get rs minus j omega 1 L sub s. But we can, look at just the real term and then the imaginary term separately. So we'll get rs over rs squared plus omega 1 squared L sub s squared as the real part. And then we'll get a j omega 1 times c sub p in parentheses minus L sub s over rs squared plus omega 1 squared L sub s squared. Are we with me so far in the math? Grunt your approval. Good, good. Want to make sure I'm not going too fast because this is a more complicated example. Yeah. The instructor is actually doing something that isn't just all series or all parallel. Like, I'm gonna try a little harder today. So we see the real part and we see the imaginary part. So by our definition of what happens at resonance, we need the imaginary part of the admittance at that frequency. In other words, we need the susceptance at that frequency to be equal to 0. So in order to get this equal to 0, omega 1 can be equal to 0, or what's in parentheses can be equal to 0. We have an arbitrary omega 1. We can't just let omega 1 be equal to 0. So we assume it's some sort of non-zero value. So we should make the other term in parentheses equal to 0. Or in other words, c sub p is equal to L sub s over rs squared plus omega 1 squared L sub s squared. Now, here's what you would do. You would multiply the denominator out, you would get, some term with ls squared. You'd be left with an ls on the right-hand side, and you'd have some, term that doesn't depend on L sub s at all. That's a quadratic equation. So we bust out the quadratic equation. I don't go through all of the machinery here. You've done the quadratic equation with MOSFETs. You've done the quadratic equation, with RLC circuits before. Unfortunately, I explained to my parents, like, oh yeah, this is a class that actually uses the quadratic equation. Like, you can't just forget about it. So they thought that was wild that, yeah, we actually solve quadratic equations. Not so much my dad, but my mom definitely. But you solve this out and you'll get L sub s equals 1 plus the square root of 1 minus 4 omega 1 squared r of s squared times c sub p squared all over 2 omega 1 squared c sub p. Now, we could just stare at this equation and, just accept it as is, or we can try to apply a little bit of insight. So let's pretend for a moment that this term wasn't here, this subtraction under the radical. We would get 1 plus the square root of 1, which is just 2, all over 2 omega 1 squared c sub p squared. So we would get 2 over 2 cancels out to 1 over omega 1 squared c sub p. Now, you move the ls to the denominator of the right side, move the omega 1 squared to the other side, take the square root. You would get omega 1 equals 1 over square root ls c sub p. And you're like, wait a minute, that is just the natural frequency, the undamped natural frequency of the circuit, omega naught. So you would get that the resonance frequency we're trying to establish at omega 1 is just omega naught. If only we didn't have this term under the square root. So why do we have a term under the square root? Because the circuit isn't entirely in series and parallel. There's some sort of correction term that has to deal with the fact that, C sub P is not in series with the other elements. It's actually in parallel. So we get this sort of, I guess, parallel correction factor right here. 4 omega 1 squared rs squared c sub p squared. So that's the answer to this problem. So I want to remind you that this was a design problem. We could choose to make the omega resonance frequency omega r equal to omega 1 because ls was unknown. If I give it to you the other way around and say, given ls, rs, and c sub p, find the resonance of that, circuit, you would just find the admittance, figure out what makes the susceptance go away and call it good. You'd solve for the omega value that does that, which is a different ball of wax. I mentioned the correction term. So this is the resonance frequency that will maximize power transfer. So if you apply the resonant, if you apply a sinusoid of this frequency, you get the maximum transfer between the source and this resistance right here, Rs. However, it's still not optimal. The optimal solution would be to get, C sub P to be equal to 0. In that case, you wouldn't have anything here. You would just have a series RL circuit. But the fact that you have something that basically shorts out the resistance at high frequency means you have to deal with that. Oops, I'm sorry, you're not meant to see that. Let me open the lecture set again. Any questions about this example? Is maximum power transfer usually the goal? I would say it's always the goal. Most of the time, you're trying to minimize your losses more so than you're trying to maximize power transfer. Because if you recall from maximum power transfer theorem, it's you're choosing values such that you maximize the transfer of power. However, that doesn't necessarily mean you're minimizing your losses. It's usually at a very lossy point in your circuit. So generally, you'd rather reduce your losses than maximize power transfer. Does that answer your question, person who is not named? Because you appear as C0. Oh, you're Aubrey? Oh, okay. You must have had to change your name for like ECE 270 or something like that. Because you appear as C019 to me. Okay, Mom. All right. Sorry, I did not know you, but I can't tell who you are if you don't have your name show. Without any further questions, let's go ahead and get back to resonance in the second order systems. So, I remind you, the simplest resonance circuit must have some inductor and capacitor to exchange magnetic electrical energy with each other. But they can have an arbitrary number of resistors. So let's look at the pole zero plots of different RLC circuits. So the first one is not an RLC circuit. It's actually an LC circuit. It would be called undamped. If it's just LC, there's no resistance. So there's no attenuation of the sinusoid over time. That means, the poles are going to be right on the imaginary axis. Also note that I am marking omega naught equals 10 radians per second on this chart. And we will see why as we go on. So if omega naught was 10 radians per second, that'd be 1 over square root LC. We'll see that it still plays a major role in the circuit, even if it's not a given frequency of any given signal. So now let's look at an underdamped circuit. So for an underdamped circuit, we will get exponentially decaying sinusoids. Remember, S1 sub 2 or S1 and 2 are going to be equal to lambda 1 and 2, where S is basically our pole locations. Negative sigma p plus or minus j omega d. Or that's the simple way of writing it. A lot of people on homework 3 were writing a lot more complicated expressions. That's okay, but just remember to simplify them based on your case. So remember that sigma p squared plus omega d squared equals omega naught squared. And if you think about this, this is basically saying your x coordinate, squared, plus your y coordinate squared equals some constant. X squared plus y squared equals a constant. Wait a minute, that's the equation for a circle. In this case, the circle is going to have radius omega naught. So that's why I'm taking the trouble to mark omega naught. This is, a circle. And we call omega d the damped resonance frequency. It's the frequency that, the circuit will actually have the sinusoids oscillate at while they damp at, another frequency. I think I chose -8 and 6, or -8 plus or minus J6. So in this case, it would be they would be of the form, A1 cosine of 6t times e to the negative 8t plus B2 sine of 6t e to the negative 8t. Does this all sound familiar to everyone? I hope so. So now we're going to look at the critically damped circuit. So we're the critically damped circuit. We're going to have exponential decay and a t multiplier of that exponential decay, just like you saw in homework 3. So you'll get S1 equals S2 equals negative sigma p. The pole has multiplicity 2, and it's going to be right over here at minus 10. So it does still lie on this circle. It's just purely imaginary. And, you know, there's a little superscript 2 here on the pole 0 plot to denote that the pole has multiplicity 2. Note that, you know, if you look at the full equation, you know, for RLC circuit, so it's something like, you know, for the parallel RLC circuit case, it's 1 over 2 RC. Well, no, it's negative 1 over 2 RC plus or minus the square root of quantity 1 over 2 RC closed quantity squared minus 1 over LC. Notice all that simplifies down in the critically damped case. So please don't just leave your circuit like that. When your circuit's critically damped, what you get is that the term under the radical is 0, and you're just left with, you know, negative 1 over 2 RC for the parallel case, or negative sigma p. So be mindful of that. That's just me being a little bit frustrated after grading homework 3, or part of homework 3. I'm not done yet. And then lastly, what happens to the poles in the overdamped case? So we'll have distinct exponential decay terms. So we'll expect purely real poles. In this case, they're at negative 5 and negative 20. So we'll have S12 equals, you know, lambda 12, which is negative sigma p plus or minus square root of sigma p squared minus omega naught squared, where this is, you know, a positive number. Sigma p squared minus omega naught squared is positive. Such that we'll have square root of S1 times S2 equals omega naught. So this omega naught circle kind of comes into play. Nothing lies on the circle. However, you'll see that S1 and S2 are the, you know, their geometric mean is omega naught. So it would be, you know, that point right there at negative 10. Or positive 10 if you prefer thinking about, you know, the multiplication of two negative numbers being positive, as most people would. But then you take a square root, so you can do plus or minus, so it doesn't matter. So we can see, like, you know, the critically damped case, it's obviously, you know, negative 10 is the geometric mean of negative 10 and negative 10. But here, the geometric mean of negative 5 and negative 20 is also negative 10 in some sense. So do we have any questions about these pole 0 plots?
Yeah. Actually, a quick question if you go back in the diagram.
Do you want the critically damped and overdamped?
Yeah,
Or do you want...
Yeah.
Okay.
So on the overdamped one, why aren't those like the x's? Why aren't they the same distance from the omega 0 like circle?
Why aren't they? I don't think I have a... Huh?
Isn't it kind of like it's plus or minus, right? Isn't that like they're being offset from that circle?
Well, they're being offset from negative sigma p.
Is sigma p on that circle or not?
yeah, negative sigma p would be right at -10.
Right. So one of them should be like
Oh, wait a minute,
-15
wait a minute. No,
or
no, no, no,
25.
no, it's not. I need to correct myself. Because it's an overdamped circuit, we don't have a strict relationship between sigma p value and omega naught.
Oh,
They're
okay.
both free variables, more or less. They just have to say, we just have to have sigma p squared greater than omega naught squared.
Okay, that makes sense. Thank you.
So it's not on the circuit. So like, it would be whatever halfway between -5 and -20 is. So like -12.5 or something like that is sigma p. Negative sigma p would be like -12.5 then. Yeah, good question. Good question. The important thing to remember is it's not, sure, the math produces something that looks like this, but if you work out, what S1 and S2 is when you multiply them out, you get like, negative something plus something, negative something minus something. That factors like a difference of squares. So you would get something that looks like negative or sigma p squared, and then minus sigma p squared, minus omega naught squared in parentheses. So you would get negative sigma p squared, or sigma p squared minus sigma p squared is 0, and then minus a minus omega naught squared is plus omega naught. So you would get omega naught squared. So if you take the square root, you get that. So if you do work out the math, you would, by multiplying S1 and S2 together and taking the square root, you do get omega naught. So work out the math if you're skeptical. Good question. Good question. I think clearly, we could work out, RLC circuits that are more complicated than just parallel series. You can have parallel series RLC. You could have parallel series RC. You could have series parallel of all those. So like, there's like 5 other circuits of this form. 2 other parallel series, and then 3 series parallel. 8 circuits in total if you count this all in series or all in parallel cases. So, and that's just with one resistance. As you add more resistances, you get more interesting transfer functions too. Let's move on though. Let's talk about frequency response. So this is the heart of this lecture set. I titled the lecture set frequency response. So let's talk about frequency response in general. So phasors are good at analyzing how a circuit responds to a single frequency, but most real-world signals involve multiple frequencies. Voice band includes multiple frequencies. Music, you want multiple frequencies, unless you're working with a synthesizer or something like that. In just very specific cases. Any sort of sensor data is going to have multiple frequencies. So we're going to really want to understand how the circuit responds to multiple frequencies. So instead of working with a phasor at a set frequency, we're going to, look at a little more generic with generic omega. So if we look at the polar form of a phasor, we'll see a magnitude scaling and a phase shift. So h of j omega is equal to the modulus of h of j omega, and then e to the j argument of h of j omega, where modulus is, given by the absolute value function, it's the positive, it's strictly non-negative, and then the angle is somewhere between negative pi and pi radians. So here is something very important that I must convey to you for your homework purposes. So listen up. If I ask for the frequency response of a system, you must do 2 plots. You must give both the magnitude response and the phase response. So show me how the phase responds and how the magnitude responds. Don't just plot the magnitude response or just the phase response. Most people just plot the magnitude response though. And you must plot over all frequencies of interest. So, please keep that in mind as you do your homework for next week. We're dealing with complex numbers, so it takes two different graphs in order to show how a, real number input, in this case, real number frequency, produces real and imaginary parts, or in this case, magnitude and phase parts. So, we're only concerned with imaginary values of S, so we're going to stick to S equals J omega. And again, this is equivalent to evaluating the Laplace transform only along the imaginary axis. So H of J omega is H of S just if S equals J omega. So nice and straightforward. Once you have the H of S, you can easily find H of J omega. It's just an evaluation. So let's do an algebraic frequency response. So find the frequency response of the capacitor voltage in the series RLC circuit, and the response, implied being to this input voltage. Plot it on semi-log paper using a reference coastline for the input. R equals 100 ohms and C equals 0.1 farads. So whenever we talk about frequency response, it's, almost always means use logarithmic frequency scale. Whether or not the magnitude is in logarithmic scale or not depends. And since phase includes both positive and negative quantities, you always do a linear scale for the y-axis of your phase response. And specifically, what logarithm? Log base 10. You have values. Now we should be able to do this. So first of all, we'll convert the circuit into impedances. So R becomes R, C becomes 1 over SE, and then little lowercase letter signals become capital letter signals as functions of S. And we'll also have Vn of S here. And then we evaluate right here. So transfer function Vc of S over Vn of S. Well, this is just voltage division with impedances. So remember, voltage division, we'll get Vn times 1 over SC divided by the total impedance, which is R plus 1 over SC. Divide both sides by Vn, you just get the transfer function. So now we are going to simplify with S equals J omega. So H equals 1 over J omega, and you'll get 1 over 1 plus J omega RC, right? So basically we get, J omega in place of the S's here, and then we multiply numerator and denominator by J omega C just to cancel things out. But, this is just, a ratio of complex numbers. 1 is a complex number, just one that happens to be purely real. And then this is a complex number in the denominator. Just has omega as a variable instead. So now we're going to take the magnitude response, absolute value, numerator and denominator. Remember, this is important property. If you want the absolute value of two complex numbers z over w, that's equal to the absolute value of z over the absolute value of w. So absolute value of 1 is just 1. Absolute value of 1 plus j omega rc, well, it's like Pythagorean theorem. So it's going to be the square root of the sum of the two components squared. Square root of the real part is just 1, because 1 squared is 1. Square root of the imaginary part is omega rc, but that needs to be squared. So this is the magnitude response, written algebraically. The phase response, remember, if you need the phase or of z divided by w, that's just going to be the phase of z minus the phase of w. So the angle associated with 1 is 0. The angle associated with the denominator is going to be arctan of b over a, so omega RC divided by 1. But since it's in the denominator, we get 0 minus that, which is just negative arctan of RC omega. And now we're ready to plot. And we have to choose sensible bounds for the plot. So you can't just plot this once and be done. You have to try different frequency bounds until you get something that looks good. What questions do we have? Does everyone see how I got 1 over square root 1 plus RC omega quantity squared, and how I got negative arctan of RC omega? You're not super clear how you got the phase response. Okay. So what is the angle that is associated with the complex number 1? 1 plus J0. That should just be 0. Very good. What is the angle associated with 1 plus J omega RC? No. We need the full imaginary part, which includes omega. So we need to have omega RC. But remember, if I have a real number or a complex number, z equals a plus bi, or excuse me, jd, then we have that, angle of z equals arctan of b divided by a. Right? So this is how you convert a rectangular form number into a polar form number. This should remind you of when you worked with phasors in ECE 20001. You got really good at going back and forth between polar and rectangular and polar and rectangular. Since we're dividing, we want to get into the polar form. Anyway. And now, when you want to take angle of z divided by w, that's equal to the angle of z minus the angle of w. That's, if you take, e to the j angle z over e to the j angle w, that's equal to e to the j quantity angle z minus angle w. So we're going to get 0 minus arctan of RC omega, which is just negative arctan RC omega. Does that make a little bit more sense to people? A little more clear? Yes, sir. Everyone else like, this is old hat. Or if it's not clear, feel free to visit me during office hours or any of the other TAs. They like to help too. But we can do a little bit better than just, write down math. We can plot these functions. These are, since this is a series RC circuit, we can just plot these functions with the numbers we were given. So let's look at a plot, with the logarithmic frequency axis. So here's 10 to the negative third, radians per second, all the way up to 10 radians per second, 10 to negative 3 radians per second, up to 10 radians per second. And then, you know, let's see. I guess by convention, we use degrees for the phase plot. And then here's a nice linear axis for the magnitude response. So magnitude of h j omega goes from 1, and then goes down to 1 over square root of 2, which is like 0.7071. Then all the way down, you know, asymptotically towards 0. And then here we see that our phase goes from 0 at low frequency all the way up to negative 90 degrees at high frequency. And then at that same 1/10 of a radian per second, we get negative 45 degrees. So the magnitude response approaches a minimum value of HM1, or excuse me, the maximum value as omega goes to 0, and approaches 0 as omega goes to infinity. Yep, makes sense. So it's basically saying we'll get, you know, complete voltage transfer at very low frequencies when the capacitor looks very close to an open circuit. And then at high frequencies, it looks very close to a short circuit. So we would get 0 voltage across it. The greatest drop in magnitude corresponds around the 1 decade, centered at omega equals 0.1 radians per second. And by decade, we mean an interval that corresponds to 1 factor of 10. You know, we talk about decades when we're dealing with logarithmic x-axes. So from about, you know, 3 times 10 to the negative 2 right here, down to 3 times 10 to the negative 2 right about here, or 3 times 10 to the negative 1, I should say. This is where the greatest drop in magnitude occurs. So the phase response approaches 0 degrees as omega goes to 0, and reaches down towards negative 90 degrees as omega goes to infinity. Yep. The greatest change in phase occurs for the 2 decades centered at the value negative 45 degrees, where it was 1/10 of a radian per second. So from 0.01 radians per second to 1 radian per second, it almost looks like a line down. So for 2 decades. So at very low frequencies, you know, outside of this range where we talk about the phase, that looks just like a resistor. There's 0 phase offset. And then the circuit looks just like the capacitor for omega greater than 1 radian per second, where, you know, the phase is negative 90 degrees, as we would expect for a capacitor. Just remember 1 over j omega c, that 1 over j is equal to negative j, which is the same thing as saying negative 90 degrees. And then what makes omega 1 equal, or omega, or what makes 1/10 of a radian second so special? That is exactly the frequency corresponding to 1 over RC, which is our time constant. So that's where we get this 1 over square root of 2 value, which is a very important value because 1 over square root of 2 corresponds to half the power. It also corresponds to a 45-degree when it's the most indecisive between behaving like a resistor and behaving like a capacitor. There's a lot to be parsed out of that slide. So, you know, I would say slide 23 is, you know, definitely a slide that you should ponder for a bit on your own when doing your homework. What questions do we have? Hearing no questions, I'll move on to the graphical approach to the frequency response. So we talked about algebra. Now let's talk about graphical. So we'll interpret each of the complex factors in the fully factored form of h of j omega as a vector in the complex plane. So this is the factor transfer function, z1 up to zm in the numerator, p1 up to pn in the denominator, and everywhere we had an s, we plugged in j omega. But you can interpret, this, each of these terms, for example, like this term right here, as a vector. So it points from, a vector from z1 up to wherever 0, j omega is. And then this factor right here would point from p2 up to where j omega is on the imaginary axis. Like, that's kind of neat. We normally don't think of, we try to avoid thinking of complex numbers as vectors after a certain point, but we can kind of go back to that mentality and think of complex numbers as vectors. So the magnitude response is going to be the product of the lengths from each 0 divided by the product of the lengths from each pole. So here we'll see that, we'll have a factor of k out front, and then we'll have, j omega z in absolute value divided by the product of all the lengths from, PL to j omega on the imaginary axis. And the phase response, because, the way this all works is, the product of complex numbers is equal to the sum of the phases, and then division corresponds to subtraction. So the phase response is, the sum of the vector angles from each 0 to 0, j omega minus the sum of the vector angles from each pole to 0, j omega. Now this seems like a bunch of nonsense at first until I think you see an example. So here's one example that hopefully illustrates what I'm talking about. So find the frequency response at the point omega equals 1 radian per second. So here is the transfer function. We'll rewrite it factored out. So we'll get s minus 2j, s plus 2j in the numerator. And then we'll get s plus 1 times quantity, s plus 1 plus j, plus quantity times quantity, s plus 1 minus j. So we'll rewrite the transfer function of factors of complex roots. We'll draw vectors on the pole 0 plot. So for example, we'll have a 0 at minus 2j, and we need to draw the vector to j omega, where this is at 1. So this is going to be a vector of length 3 at an angle of 90 degrees. The vector at 2j, or the 0 at 2j, is going to be pointing down to j omega, so it's going to be a length of 1 with an angle of negative 90 degrees. The pole at negative 1 points to the j times 1 radian per second. And it's going to have length square root of 2 and an angle of 45 degrees. You use Pythagorean theorem to figure this out, or just notice that's a 45, 45, 90 triangle. The pole at negative 1 plus j is going to have, length 1 and angle of 0. And then more complicated, this one right here, the pole at negative 1 and then at minus j is going to have a length of the square root of 5, because it's 1 squared plus 2 squared under the square root. And then the angle is going to be, arctan of 2 over 1, which is like 63.43 degrees. So the magnitude response, we said, is going to be, k is equal to 1 times the product of the lengths from the zeros, so that's 1 and 3, divided by the product of the lengths from the poles, 1 square root of 2 and square root of 5. So that's equal to 3 square root of 10, or, the magnitude of h at J1 radians per second is equal to about 0.9487. And the phase response, well, that's going to be the sum of the pole of the zero angles, plus 90 degrees and minus 90 degrees, minus the sum of all the pole angles, 0 degrees, 45 degrees, and arctangent of 2. Work this all out, and you get that the angle at J1 radian per second is equal to 108.43 degrees. What questions do we have? No, 0 j comma j omega is the point. 0 comma 0 is the origin. Because we're evaluating at a j omega, we expect something along the imaginary axis to be the tips of all of our vector arrows. Please use degrees for your phase response. Or if you must use radians, mark where pi occurs and pi over 2 occurs at the very least. Like those need to be ticks, David. How did we get to the point we're measuring to? We were just told that we need to evaluate at that point. Well, Pranav, if you have a pole and a 0, which are at the exact same point, they would just cancel out of the numerator and the denominator. So it's like neither are there. They annihilate each other. What questions do we have? Those were good questions. I like them. Hearing no more questions, let's go ahead and call a lecture for today. Thank you very much for listening. Goodbye, everyone. I'll see you in office hours. Salam, let's just meet during office hours since we're so close to it. Is that okay? All right. Goodbye, everyone.